Hey class, and welcome back. To introduce this next unit, I'm going to do one of my favorite demonstrations because we're going to be learning about angular momentum. You might remember that in a system free of external forces, linear momentum is conserved. What we're going to learn now is one, what angular momentum is. It's based on the rotational mass or rotational inertia of an object and its rotational velocity. And we're also going to see and observe that in an isolated system, one free of any net external torque, angular momentum will also be conserved. One of the most common examples you might have seen is picture a figure skater. If you've ever seen a figure skater begin to start spinning, as they pull in their arms, they begin spinning much more rapidly. As they change the rotational inertia, they change the rotational speed as well because they're in an isolated system. Emphasis on the isolated, on ice. Okay, anyway, I want to do a demonstration of the same idea. So I have here my fun spinny chair that is pretty much frictionless. As I sit on it, once I lift my feet off the ground, will have an isolated system. I'm going to start spinning my bike wheel, which has rotational inertia, and I'm going to give it rotational velocity, so it will have rotational momentum or angular momentum. So I'm going to get it going. It has angular momentum. All right. Now I'm going to lift my feet off the ground to create an isolated system. And if I change its angular momentum by changing its direction, I should also experience a change in angular momentum. So good. If I go back, I stop. I turn it again and I begin spinning again. Just by changing the direction of the wheel, changing its angular momentum, I experience an equal and opposite change in angular momentum as well. Another cool thing to see, all right, again, it's spinning, it's got angular momentum. If I stop it, I should absorb its angular momentum. So I'll lift my feet off the ground, I stop the wheel, and I take on its angular momentum. So cool, right? But that's just the beginning. The best part's still to come. So the idea of angular momentum and angular impulse, which we'll be learning in this unit as well, govern what are known as gyroscopes. So you've probably seen when you spin a top, it spins very rapidly, but as it spins, it also wobbles, going through sort of a larger, slower rotation. That is known as gyroscopic procession. I'll be explaining and defining it more in future lecture videos, but what I want to show you right now is an example of that and how it helps us ride bicycles. So here's my bike wheel. I have tied here, it might be hard to see, but there's just a piece of fishing line, okay? If I hold the fishing line with the bike wheel and let it go, the fishing line generates a torque, gravity pulls down on the bike wheel, and it rotates and it falls sideways. So now I'm gonna do the same thing, but with the wheel spinning. So I get the wheel spinning, hold it straight, and hold my fishing line. Let's see what happens. Oh, look at that. It doesn't fall over. Instead, it goes through gyroscopic procession. It continues to go around in a circle. This is what a bike wheel does. This is what a bike wheel does as well. Hopefully you have stronger fishing line if you ever try this demonstration at home. So anyway, in this unit, what we're going to be doing is learning about these ideas of angular momentum and applying them to various problem-solving situations. You'll also be learning a little bit about how linear momentum and angular momentum are related. So get excited, keep practicing your good problem solving, and let me know if you have any questions.